Welcome back. We are talking calculus and limits, and we're picking things up exactly where we left off in the last segment at the bottom of page 2 with example 4 in the limits packet. And take a look at this function. I think that'll help us answer this question. You've got a piecewise function, and I want to graph it. It is pretty ordinary, y equals 2, everywhere except for when you're at the x value 3. I'm going to put an open dot here and a hole in the graph. When x equals 3, this function has a closed-in dot at 0, and that's what that piecewise function would look like. And the question is, I see there's a little gap in the graph. What are you going to call the limit as x approaches 3? First of all, does it exist? And second of all, what number would it be? Are we up at this y value or are we down at that y value? Well, think of the analogy I was proposing for you to use in the last few examples. You've got one person who's walking along the function trying to get to his friend going this way. The other person is approaching that x value from the right, trying to walk to his friend going that way. Where are they going to meet up? They're not going to meet up down at 0. They don't have the ability to hop down. They're going to meet up at that open dot, which is at y equals 2. So here's a great example where the limit is up at the y value 2 versus the function value. If somebody said, okay, fine, you found me the limit at 3. What is the actual function value at 3? We have to go back to all our old rules and say, well, that's the closed-in dot. It's going to be 0. So there is a limit. There is a function value. They're not the same thing. On the next page, page 3, we talk about discussing the existence of limits. Here's a piecewise. Feel free to pause the video here so you can think about what this would really look like, maybe even make a table of values. I'm going to do this a little quicker so we get a visualization of it. It's going to be 2 times 1 when x is everything above 1. At 1, we have a problem because you'd be dividing by 0. But you would be getting outputs on this function that are all positive 2 when you're above 1. And they'd actually all be negative 2 when x is a value below 1. You have a piecewise function that has a huge jump in the graph, a big gap between the two sides. And the question is there a limit? Well, this is kind of a sad story. Let's say we have a girl who's walking along the function. We'll give her a little skirt. And she's trying to meet, I don't know, somebody that she has a crush on. So we'll put a guy up here. And he's trying to meet up with her. And this is a tragic story because they don't have the ability to jump. They're not walking toward the same spot, right? The two limits, the left side limit, the negative 2, and the right side limit, positive 2, do not agree with one another. So we got to think to a classic Lindsay Lohan movie from 2004. You heard it first here, Mean Girls. In the end, she's in the mathletes, and she proclaims at the end of the competition, the limit does not exist. And that's what we say here. The limit D-N-E, it does not exist. You can think good thoughts about Lindsay Lohan every time you say it, but it's because the right side and the left side do not agree with one another. What about these other? I chose 6, 7, and 8 to be rational functions where you're going to notice each time I'm having x approach a value, it's at some problematic value that's outside of the domain of the expression. Plugging in 0 here would be problematic, 1 divided by 0. Well, 1 over x squared, if I think about the shape of it, it's going to give you a function that looks like this. It's always positive, always above 0, but it's got a vertical asymptote that just outlines the y-axis. Here is more of a philosophical question. If two people were walking along this function from the left of 0 and from the right of 0 and trying to get to each other, would you agree they're walking the same way? Well, sure. They're both going up toward positive infinity. Would they ever meet? And I feel like philosophically, you have to say no, right? Because would you ever reach infinity? I mean, you can't really tell me you can or you can't because none of us have ever gotten there, I don't think. But there are 2 possible answers to number 6. You can tell me the most specific way to answer this is to say infinity or positive infinity because that describes the left and the right-hand behavior of the function. Both sides are approaching positive infinity. But because we're putting an infinite answer here, it is weird to call infinity a limit. I mean, by the nature of infinity, it's the lack of a limit. You keep going up and up and up. So a safe answer and an accurate answer is to say that in this one, there is no limit. The limit does not exist. The two sides do agree with one another. I want to skip over to number 8. So we see a different type of picture. This one, if I know my rules about finding asymptotes, you set the denominator equal to 0, and it's bottom heavy, so it'll also have a horizontal asymptote. And all those asymptote rules are really going to come into play when we talk about limits as well. They're going to come in handy. You're going to have a hyperbola graph that's going to approach those two branches from the left and the right side of x equals 5. So that's a rough sketch of it. The question is, can we put anything for the limit? Should we put that it doesn't exist because the two sides really don't match? Or is there some type of infinity that we could pick for the left and the right side limit? Picture a guy trying to get to his friend. One guy's walking down the function forever. The other guy's walking up the function forever. This limit at 5 absolutely positively does not exist. And unfortunately, there's nothing else we can say about it. When you put x goes to 5, you're assuming you're talking about from both sides, from the left and from the right. And one is approaching negative infinity, the left side limit. The other is approaching positive infinity. They do not agree. The limit does not exist. And that's one of your main cases. A vertical asymptote is going to be one of the main circumstances where there is a lack of a limit. If, just to refresh those rules for ourselves, if the function approaches positive infinity or negative infinity, if it grows or decreases without bound, as x approaches a value c from either the right or the left, you have a vertical asymptote on the graph. And that means DNE is a really safe answer for the limit. Keep this fact in mind for later. It's not going to be that important until a lesson down the road when we get into algebraic ways to calculate limits, but now we're kind of just talking about graphs. If you do an initial plug-in, and that plug-in of the x value gives you some non-zero value divided by 0, that's another algebraic dead giveaway that there is no limit there. There is going to be a VA. Here's what I mean. If I take the example we just did and I plug in 5, I get 1 over 0. I get a non-zero number over 0. The limit does not exist. Same thing here. If I plug in, if I had done number 7, we skipped this one, but negative 2 over 0 would mean the limit does not exist. DNE is going to be a good solution for 7. Versus a couple examples from the last page. If I had plugged a 0 into number 2, I would get 0 over 0. If you get 0 over 0, that's not the case we were just talking about. It's not a VA, it's a whole, and we did get a limit. Keep that in mind for later, though. At the bottom, one trig example. So this is a crazy one. You could use a table to kind of see what this thing is doing, but it says sine of 1 over x, and I just want to think about it for a second. If I think of a unit circle, and taking the sine value. Sine is so cyclical, right? It bounces from the sine being 0 to 1 to 0 again to negative 1. It keeps going and going and going as x gets bigger and bigger and bigger. And as 1 over x changes from value to value, sine of 1 over x, I'm going to say is going to oscillate between two fixed values, negative 1 and 1. 1 is the highest it'll ever get to, this whole expression. Negative 1 is the lowest it'll ever get to. And it's going to bounce in between any number of times as x is approaching 0. There is going to be a problem with this limit, and let's jump straight to a graph. I'm going to go, since I know this is a trig function, I'm just going to check my mode first, make sure I'm working in radians and function mode. Quit out and clear out the equation that we had in from the previous example and type in example 9's equation. So I'll use sine of 1 over x. Okay. Brace yourself for what's about to happen. Not all graphs are just so cut and dry. This one might be a little bit spooky. Let's see what it looks like. I'm going to graph it on a zoom 6 for starters, just negative 10 to 10 to see if I get any error message, if there was a plot I had to turn off, or see how it looks. On a standard zoom, negative 10 to 10, this is the graph you should see. What does it look like? I don't know. I'm going to have to zoom in a bit so I can really see what's going on in the middle. I see some funny business in there. But before, it looks like there is a horizontal asymptote running straight across the graph. It looks like 0 is approached to the two outsides. Maybe is the origin the limit in the middle? If two guys were walking along the function, would they hook up, connect at the origin? Let's zoom in. I'm going to hit window, and I'm going to go, I'm going to zoom in really fast. Actually, let's do this in stages. Let's go negative 4 to 4 for the x's, and we'll go negative 4 to 4 for the y's. And then after that, I want to zoom in further so we can see the change here. So I'll hit graph. Ooh, it says error window range. Let me see the mistake that I made. I'll go window, and then how about I go negative 4 to 4? Does that look better? So graph. Do you see more of it? Almost looks like a heart monitor type of thing in the middle. It's bouncing up, down, up, down, up, down. Is the limit still 0? Let's zoom in even further. This is where it gets really strange looking. So I'll go window. How about we go just negative 1 unit to positive 1 unit for the x's? Same thing for the y's, negative 1 to 1. Let's make that 1. Hit graph. It is a mess in between there. This thing is impossible for you to sketch a graph of it. I call it an infinite oscillation because as you get closer and closer to zero, we could zoom in further and further and further, and we're just going to have a mess on our hands. There's no way to tell that it's even ever going straight through the origin. I know I'm getting a little bit carried away with this. I'll zoom in one more time. The limit does not exist. This is a problematic infinite isolation for a transcendental function. So here's my best sketch. Please don't throw tomatoes at me. That's what it's kind of looking like. Can you write that phrase there too, just to remind yourself? This is an infinite amount of oscillations. Infinite oscillation between two fixed values. And what's important is it's not just the oscillation of the normal sine curve that's pretty predictable. As you get closer and closer, as you zoom in further and further, you see this thing bouncing up, down, more and more times. So here's another case where the limit does not exist. And I'm pretty much done. I think that's a good place to end it, but I do want to summarize our findings on the next page. So the next page is just a good summary of the 3 cases where we found there to not be a limit. So the limit of f of x as x approaches c does not exist when, in one case, f of x approaches a different number from the right side than what it does on the left. This is called a jump in the graph. We saw that at least once, I think, with a piecewise function. If f of x, will say, increases or decreases without bound as x approaches c from either side, that's going to be a VA that we talked about too. And you'll say there is no limit there. The limit does not exist. Sometimes there are cases where you can pick a type of infinity to say for your answer. How about number 3? This is what we just found. If f of x, we're going to say, oscillates between 2 fixed values, 2 fixed, as x gets closer and closer to c, like we saw in sine of 1 over x, you'd actually see the same thing in cosine of 1 over x. As x approaches 0, in those type of transcendental functions, it's an infinite oscillation. There will be no limit. And for my visual learners, right, here's a few diagrams of those things that we just found. Limits that do exist. Here's a normal S-curve. And in the middle, I'll say, as x approaches c from both sides, the limit of f of x is going to be that y value L. And even if there's a hole, we're still okay. You could have an open dot where you want your limit to be. We found this early on. And maybe a closed-in dot way above it. And the limit, just disregard. Who cares about f of c? F of c is way up here, but the limit is where the 2 people would meet up walking along the function. The limit's still going to be L. So holes don't cause you to not have a limit there. But the cases that we found where you don't have a limit are going to be a jump, let's say. So let's say from one side of C, we're approaching one left-hand limit value, and we've got a whole nother value from the other side. At a jump, we'll say the limit definitely does not exist. And that is a jump in the graph. I wanted to draw 2 pictures of cases with asymptotes. One where you could actually put a type of infinity. So let's say we have an asymptote at x equals c, and maybe both sides are just rising, right? Increasing without bound. You can put positive infinity for this answer, or you can put dne. And there's lots of times with vertical asymptotes that you really just can't put anything. And what I find is the safest thing to write if you know you're at a VA is does not exist, because you know that's an accurate answer. So from this side, you're decreasing forever. From the right side, you're increasing forever around x equals c. Nothing you can say about the limit. Does not exist. And these are just 2 little pictures where a VA would happen. And then lastly, the one that's kind of hard for me to draw, the infinite oscillation. So something like sine of 1 over x is just going to bounce indefinitely, and the limit does not exist. Like that. Okay. Enjoy the rest of your day. Take it to the limit today. I will talk to you later.